Hi everyone. Uh, this is the second supplemental lecture that I have, and it's on source transformation. So we talked about source transformation, but I wanted to show you some examples to illustrate how we might apply the principles that we use in source transformation, how we can get results. And hopefully through these examples, you see the mechanics of how we can apply this technique. Again, it's not a totally independent technique because it is related on things that we have learned. But the point is that it allows us to simplify circuits so that we have simpler circuits to write equations from. So that's the main point of source transformation. So let's take a look at this problem. In this problem, you're asked to find the power supplied by the 24-volt source. So when we talk about a power supplied by a source, we're talking about the amount of current that in this case, a voltage source you're talking about the amount of current that the voltage source pushes to the rest of the circuit. In other words, current that's leaving the positive terminal. Again, if we had asked for power absorbed, we would be asking for the current going from the plus to the minus terminal. But since this is the power supplied, we want the current that's leaving the 24-volt voltage source, the positive terminal. So in effect, what we're really looking for is the current that's leaving the 24-volt source in the direction indicated. And once we find that current that I've labeled as I-24, then it's a simple matter to find the power supplied by the 24-volt source as simply 24 volts, the voltage V, times the I. That's the current that's leaving the positive terminal. So that's basically I-24. So basically, if we find I-24, we really would have found V supplied. So this problem breaks down into just finding I-24. Now, with source transformation, there is the method involves basically going through series and parallel combinations of resistors, voltage sources, etc. In effect, if you think about it, the most basic transformation is going from let's say a series voltage source and a resistor to a parallel current source and a resistor, and we can also go the other way as well. So as we go through these kind of transformations one after the other, you'll see that the circuit simplifies quite a bit. Now, in this problem, since we're interested in I-24, it's best to make sure that we leave that branch, that the current that we're looking for, alone. So basically, it's best that if we leave that 6 ohm resistor, that branch alone, and work on the rest of the circuit. So what we're going to do is we're going to start on the right actually and work ourselves to the left. So what we're going to do first is to look at these two pairs of terminals right here, okay? And we're going to transform the circuit to the right of that, and then simply redraw the circuit and keep transforming basically. So if we do a source transformation on the circuit to the right, we'll have a 2 ohm resistor in series with a voltage source, and the voltage source value will be determined by the current source value, 18 amps, right, times 2 ohms. So in effect, what we have here is a 36 volt resistor. So this will replace everything to the right of those two circles, but the things to the left are exactly the same. Okay, so we can simply go ahead and redraw everything to the left. Again, this involves a little bit of patience because we do need to redraw. Nevertheless, it's a straightforward thing to do. And remember, when we do source transformation, we're really doing the algebra on the schematic itself. So here's the 6 ohm, the 3 ohm, 4 ohm, here's another 6 ohm, and here's the 1 ohm, right? So what happens now? Well, what we see now is that we see that these two resistors are in series. So 1 and the 2 ohm are in series. So what we're seeing there is basically a 3 ohm resistor. And what we note there is that, again, if we look to the right of these terminals, okay, these two terminals that I drew in orange there, what you see is a 3 ohm resistor in series at a 36 volt voltage source. Well, we can transform that. We can apply source transformation to that. So if we apply source transformation to that circuit, what we'll have is the following. We can do a 3 ohm resistor in parallel with a current source, and it's pointing up in the same direction as the positive terminal, and the value of this current source will be 36 volts divided by 3 ohms, right? So this current source is actually 12 amps. Okay. Now everything else to the right of these dots, sorry, the left of these circles, is the same. So let me just draw them as they are, right? So what we have there is we have our 6 ohm, we have our 4 ohm, we have our 3 ohm, we have another 6 ohm. Again, it's a little bit tedious maybe sometimes to redraw it, but nevertheless, that's a part of the analysis, so we do it. So that's what we have right now, okay? As you can see, the circuit is slowly getting simplified, slowly, bit by bit, but nevertheless, it is getting simplified. Okay, so what do we have next? Well, now what we notice is that these two resistors are in parallel. So 6 parallel 3 is what? Product over the sum, 18 over 9, that's 2 ohms, right? So now what we have, if you look to the right of these two circles, okay, what we have is a circuit that is a 2 ohms, right? 2 ohms in parallel with 12 amps. So that's our equivalent circuit to the right. Well, we can transform that, right? We can transform that into a series resistor, right, of 2 ohms in series with a voltage source. So it'll look basically then like this, right? So let's just draw it. We have the 2 ohms in series with a voltage source. What's the value of the voltage? 12 amps times 2 ohms. This will give us 24 volts, right? And then to the left of these open circles, we just draw what we have, right? So it's just a repeat. So we have a 4 ohm resistor, series 3 ohm, right? And then we have a 6 ohm, we have a 24 volt source here. Here's your I, the current that's leaving the 24 volt source, right? So that's all we have. What do we see now? Well, what we see now is we see that the 4 ohm and the 2 ohm are actually in series. That's simply 6 ohms. So in effect, again, if you look at these 2 points here that I'm drawing, these 2 circles, if we look to the right of those, we see a 6 ohm resistor in series with a 24 volt source. We can transform that. So keep doing it. You know, it's kind of redundant a little bit, but that's what we do. We just keep doing it, and you'll see what happens. And of course, I'm talking way too much. Of course, this is done a lot quicker than what I'm making it, but I'm trying to talk you through it so you realize what we're doing, right? So, well, made a mistake here. Hold on, I'm going to draw a parallel. It's not a series. Let me simplify. Simply erase this. Okay. Hang on with me. Okay, so what I have is, I have these circles, and I'm going to replace it by a parallel equivalent. So that means I have a 6 ohm here. In parallel to the current source, it's pointing up. It's pointing up to the direction that the 24 volt source is pointing to. What's the value of the current? It's 24 volts divided by these 6 ohms, right? 6 ohms. And what is that? That's simply 4 amps. Okay, so now this is an equivalent circuit for everything to the right of these blue circles, and then I have just a few more elements to the right. So for example, I have my 6 ohm here, I have my 3 ohm over here, and then of course I have my 24 volt source over here. Correct? And this current here, that's my I-24 that I'm really after. Okay, what do I see here? Well, I don't have to tell you how this goes, but you can kind of see the pattern here, and it's good to understand the pattern, good to understand what what we kind of expect out of here. Is that these two resistors here are in parallel. So I have 3 parallel 6. We've seen this before. This is simply 2 ohms. So what I have is, to the right of these orange dots that I'm drawing on the circuit, to the right of those, I have 2 ohms in parallel with 4 amps. Well, I can make that into a voltage source, right? So you can make it into a simple voltage source. So what do I have? Well, I can replace everything to the right of those by a series resistor of 2 ohms, right, in series with a voltage source. And value of the voltage source is 4 amps, right, times 2 ohms. That makes it simply 8 volts. Correct? That's what I have. And then the rest of the circuit. Right? The rest of the circuit, again, is going to be 6 ohms over here, 24 volt source over here, and what I'm looking for is this current. Again, if I want to, I can simplify this more. I can combine the 6 and the 2 in series. They share the same current I-24, but I can actually solve my problem right here, because normally a one-loop circuit or a one-node pair circuit, as I mentioned many times, is the simplest circuit you can have, right? Pretty much. So if you look here, I-24 is the current that's flowing to 6 ohm, but since this is one loop, right, I-24 is also flowing over here, right? I mean, it's the current that's flowing through the circuit clockwise this way, and that's the current that we're after, because if we know that current, we just go back and plug it in to the above expression that I've scrolled down. You don't see anymore, but it's basically 24 volts times I-24 is the power supplied by the 24 volt source. So how do I do this? Well, very simple. Apply Ohm's law, right? So if I, from here, that you realize that the voltage source, the voltage across the 6 ohm, this voltage is 6 I-24, right? And the voltage across the 2 ohm is 2 I-24, right? Voltage drops in the direction of current flow. And I simply apply KVL clockwise, and I'll do sum of the voltage drops equals sum of the voltage rises. Or the other way around, sum of the voltage rises, sum of the voltage drops, doesn't matter. So if you look over here, what are the drops? Well, again, if I go clockwise, right, I'm going clockwise, 6I24 is a drop, 2I24 is a drop, right, these are all in volts, 8 volts is a drop, right, and that equals the rises, and again, 24 is a rise. So this is the expression that we get in terms of I24. So again, what does it give you? 8I24 is equal to 16. Or what you get is that I24 is equal to 2 amps. That's what we get. Okay. Now the problem asks for power supplied by the 24-volt source, right? So to get back into that, right? So the power supplied by the 24-volt source is equal to 24 volts times I24, right? So it's 24 volts times 2 amps. That becomes 48 watts. So that's the final result. So I hope you see that it's quite straightforward, and you know, we really didn't write any equations, right? The only equation I wrote down was at the very end, and that was like simple KVL equation and everything else. So when we're redrawing the circuit, we're actually doing the algebra. You know, it's kind of equivalent to doing the algebra. So it's actually a good trade-off, because if you look, what are the kind of operations I did? I did series resistance, parallel resistance. I did like V over R to get an I, or I did I times R to get a V, right, for the sources. That's all I did. So it's a good trade-off if you think about it. So it's a lot more difficult to make mistakes when you redraw the circuit consistently, rather than just equations, which are a lot easier to have, you know, mistakes sneak in, plus sign sneak in, minus sign sneak out, you know, subscripts drop out, things like that. So that's why source transformation is quite a nice method to keep in mind to simplify circuits. Okay, so let's do another one. Okay, so here's another circuit. Again, in the circuit, you know, look at it. There's 3 sources, 2 voltage sources, and you see 1 current source. So let's apply source transformation to find Vx. That's what we're being asked to do, is to find Vx. So let's do that. Now, how do we suppose we do that? Well, again, I said again one more time. Can't get rid of it. What do we do? Well, you know, this method basically involves you to work things outside of the branch you're interested in. So if I'm interested in Vx, I should work on things to the right of Vx in this case. So I should try to simplify everything to the right. Okay, and one obvious thing that stands out is, okay, I can, again, just like before, I can work. Okay, I should be able to work from right to left. In particular, if I start right over here, if I look at these 2 terminals and look at to the right, I mean, I have a series resistance with a voltage source. I could quickly change that to the resistance value, the 6 ohm resistance value, right, in parallel with a current source, right? And the current source value will be 12 volts divided by 6 ohms, or it'll simply be 2 amps, right? So this replaces everything to the right of terminals that I've shown here. Sometimes it might help you to identify them as, let's say, AB or something like that, just to make it clear. It's not always necessary, but sometimes it helps, okay? And then everything to the left, we just draw as is, right? So we just draw the circuit this way, Okay, so we have a 3 ohm and the 2 amp pointing up. Right, we have the series voltage of 6 volts, and then of course we have the 1 ohm across which is marked the voltage Vx, which we're interested in. So, but this is the first step. Now, here in this step, if we look at the circuit now, we see not only one, but we see two simplifications. And let me point those out to you. Okay, the first thing you see is that there's only two terminals here, right? So if I point it out, note that there's only two terminals in where I'm going to show you right now. So basically, if you look over here, right, this is one terminal. Here's another terminal, right? So everything that's between those two terminals are in parallel. So 3 ohm, 6 ohm, 2 amp, and the other 2 amp, they're all in parallel, right? And of course, I cannot combine I can't do 2 amp parallel 6 ohms necessarily, but I can do, right? I can take the 3 ohm and the 6 ohm. In parallel, I'll have 2 ohms. I can do that. Furthermore, both of those 2 amp sources are pushing current from node B on the bottom to node A on the top. Their net effect is to push a total of 4 amps to the top, right? So I can replace the two current sources, right? These two current sources, 2 plus 2, 4 amps up, right? So that's actually going to be quite a simplification there, right? Because from 4 components, we're going to go to 2 components. So you're going to see that it's going to get quite simple. Again, what I'm trying to do is I'm trying to work to replace everything to the right of these two terminals that I've just drawn, okay? This one and this one here, okay? So if I draw the circuit, right, it's going to be very simple. Very simple. I'm going to have a 2 ohm in parallel with 4 amp pointing up. That's going to be my equivalent circuit. And then when I go to the left of that, I just redraw, right? I just redraw as is. Minus plus, this is my 6 volts, right? I have my 1 ohm and Vx, right? So you can see all of a sudden how, quite simply how simply it's gotten, basically, right? Okay, what do we do here? Well, again, I think what you want to probably do is go to a one loop circuit, and we can do that if we transform the circuit to the right of these terminals by a series equivalent. Okay, so let's do that. Let's do that now. Okay, I mean, you'll notice that the steps are, the math is super simple. It's all the concept. Okay, the math is not going to dazzle you. I guarantee you with that. It's just multiplication, addition, simple stuff like that. Okay, so this is my 2 ohm, right? And there's going to be a voltage source sitting here. And its value is going to be, right, it's going to be 4 amps times my 2 ohms, right? And 2 times, that's going to be 8 volts. And then to the left, I'll just redraw again, okay? I'll just redraw like this. It'll be my plus minus 6 volts. Vx and 1 ohm. That's my circuit. Now what can we do with this? Well, actually, you see now that, 2 ohm and 1 ohm are in series. I don't want to combine them because if I combine them, then the Vx gets lost, right? Where is Vx now? If I do 2 plus 1, 3 ohm, Is the voltage across the 3 ohm Vx? No, it's not, okay? So that's why I'm keeping that separately. But if things are in series, I can shuffle things around, or I can move things around. And what I want you to, this next step is not really necessary unless you really need to see it. But, it's perfectly fine to redraw, right, in this case, and do this, right? 2 ohm. I'm going to slide my 6 volts this way because honestly, I don't really care what kind of manipulations I do to the circuit to the right of the 1 ohm, where I'm looking at Vx. Okay, and the reason I'm drawing it this way is to call your attention to the fact that these two voltages are in series. In other words, if I went to the circuit, this circuit over here, if I went there and wrote a KVL equation, I would have an equation which 6 volts and 8 volts would appear in the same equation, and they would either add or subtract or something, and there's something going on there, right? That's what I'm trying to show you. But what I'm trying to show you in particular here is that these two voltages are in series, and we can actually replace them by a single voltage source. Now, how do we do that, right? Or what's the best way to do that? Well, it's like almost combining current sources in parallel, right? It depends on what their basic effect is. So if I'm interested in these 2 points here, right, and I want to replace everything to the right of these 2 terminals by a voltage source, what would that voltage be, and what would its polarity be? Well, again, let me just call this point C and point D, for example. So if I go from point C to this point here, point E, I go up by 6 volts, right? So I'm going up by 6 volts going from here to here. And then as I go from E to D, right, I'm going down by 8 volts. Does that make sense? So then the net effect of going from C to D, right, you go up by 6, down by 8, is to go down by 2, right? So in effect, the voltage from here to here, from C to D, is actually 2 volts, right? Does that make sense? Well, how do we check it? Well, if you imagine having a little loop around here, right? Imagine going around a loop, this way. If you can imagine it, right? Does that KVL hold, right? Think about starting at D. I go up by 2 volts. I go up by 6 volts. I go down by 8 volts. I'm back to the same point. Okay? I'm trying to make I should make a big deal out of this, but these are some of the things that students get stuck in, so that's what I'm trying to point it out. The point is that I should be able to replace those 2 voltage sources to the right of point C and D by a single voltage source of value 2 volts from C to D, as shown right here. So in other words, if I redraw what I just verbally said, right, it's going to look like this. There's a redraw, not making any changes here, and then this would be 2 volts. Why am I doing this? Is because if I have this circuit and I can just apply simple voltage division, right? It kind of looks backwards because normally we have the source on the left and the V1, V2, or whatever we call it on the right. But this is the same situation, really. It's actually no different. It's actually no different because you have some voltage across the 2 ohm and some voltage across the 1 ohm. And the voltage across the 1 ohm, which we're calling Vx, is simply the resistance of the voltage marked across Vx, right? So this is the 1 ohm divided by 2 ohm plus 1 ohm, right? Times 2 volts. So that's simply 2/3 volts. Now obviously this is simply voltage division. All right? Does that make sense? So this is the final result, but you can see how one may use. Okay, again, one may use. You don't have to. How one may use source transformation in obtaining the behavior. Okay, so let's look at another problem. So this problem, find I4. Okay, by now you're getting the point. You might be even getting sick of it, but that's fine. Getting sick of it, that means you're really getting it. You're understanding it. So here we're asked to find the current I4. Right. So we're trying to find I4. Then, again, what I see is that maybe what I should do is I should find the equivalent circuit, or I should find a simplified circuit to the left of those blue dots. Okay, if I do that, then I should have a pretty simple circuit to analyze I4 from. Okay, that's the point. So when I start this problem, then I'll start on the left and work to the right, unlike the previous two problems, right? So if I do that, right away, I can start doing this a little faster now. Right away, if I look at this section right here, right? If I look at this section here, I see 20 volt in series with a 10 ohm. So what does that give me? Well, I can transform it into a current source, right? Current source of value 20 volts over 10 ohms, or simply 2 amps, in parallel with the 10 ohm. Then I just redraw the rest of the circuit. Right? Simple enough. Okay, now again, and I said again one more time, just can't get rid of it. We see a situation like what we saw before. We see two current sources in parallel and two resistors in parallel, right? Because basically, this terminal over here, this terminal over here, right? Those four elements I just mentioned are between those two terminals. So we have 2 amps plus 3 amps. Let me clean this up a little bit. So we have 2 amps plus 3 amps. Okay, so that equals, something is going on with my pens here. Hold on. So that's pointing up, right? And then we have 10 parallel with, oh my God, I don't know why this is happening. Must be in a strange mode. So I have two, I don't know, hold on. Just not cooperating with me right now. So I have 10 parallel 15, that's equal to 6 ohms. Okay, so let's just redraw. I hope this lets me redraw now. For some reason it's getting me into a strange mode here. Just a second here. Should be good. Okay, so what I have is 5 amp current source in parallel with 6 ohms, 4 ohms, volts, right? And this is the current I4 I'm looking for. What do I do here? Well, again, I want you to concentrate on looking at from point of view of going to a simple one-loop circuit. You know, this can be transformed, right, into a 30-volt source in series with a 6 ohm resistor, and then we can continue with the rest of the circuit. Let me draw that with the normal color here, black color. Okay. Right, and again, this is the current that I'm looking for. That's I4. I mean, really simple circuit, because I know the voltage across the 6 ohm is 6I4, and the voltage across the 4 ohm is 4I4, and I have a KVL again. You know, I've done this many times. KVL, clockwise, lets the sum of the voltage rise equal the sum of the voltage drops. Do it any way you like. 30 is a rise, 6I4 is a drop, 4I4 is a drop, plus 10 volt is a drop, right? From here you have 20 equals 10I4. Sorry, somehow the 10 dropped there. Okay, so I4 equals 2 amps. So anyway, sorry about the little bit of a technical difficulty at the end. I'll try to figure it out why that's happening. It might be a feature or a bug. I probably pressed something wrong, doing it live. But I hope you see that you know, it's quite simple to apply this, especially when we have just independent sources and resistors. I just wanted to show you some of the techniques, and you know, this takes quite a bit of time in class, but hopefully by the videos you see that this is actually pretty straightforward to do. I hope you go over it. I hope you like it. I hope you enjoy the YouTube videos. I know many of you like videos instead of maybe lectures, so you can watch my lectures on at Starbucks or something. Either way, it doesn't matter, as long as you know, you take the material and it's somehow useful to you. Okay, I'll stop here, and we'll see you next time.